So I welcome you all to the Spark Research YouTube channel. This is Dr. Veer Chandra, Assistant Professor in the Department of ECE. So we are going to continue to talk about this course, Analog and Digital Communication. So here we are going to talk about the amplitude modulation. Okay, so now we are going to talk about the amplitude modulation. So what is this first your amplitude modulation? Simply here you can see this is your m of t, and now here is your carrier wave, that is cos of omega ct. So this is your modulated signal. So in order to get the the linear modulation, simply multiply both of them. So this is your multiplier, so you will get the modulated signal, right? So here is in time domain, that is this is your m of t, and here is your carrier, that is how your carrier is varying carrier signal. This the bold one is your carrier signal, and the dotted is your message signal. So corresponding to your message signal, your carrier signal is varying. So that is why how we can have the amplitude modulation. In the frequency domain, this is your m of t, and now again use the Fourier transform, and this is your the Fourier transform of your this modulated signal, that is mt cos omega t. So you can have the omega minus omega t and omega plus omega t. So how can we do this exactly the calculations you can do? So m of t, suppose as for example, this is your twice of cos omega t. So you can write in the Euler's, using the Euler's formula, half of e to the power j omega t plus e to the power minus j omega t. And so m of t, this you can write like this, and then transform, like since your f of if you are converting exponential, then twice by del of omega minus omega t, and like this. So finally your m of omega is equal to nothing, del of omega minus omega m, and plus del of omega plus omega m, right? So likewise you can find out. So here we are considering only del function, but this is valid for this equation as well. Okay, so here the example, that is how are we doing your amplitude modulations using the del function only. So this is your m of t, and here is your the double sideband, and so we are thinking about to the suppress this one. So how can we do? So this is your modulated signal, that is m of t cos omega t, and so you can put the value of m of t, that is twice of cos of omega t. And then this is another important formula that you should remember, that is cos A into cos B is equal to how much? Half of cos A plus B plus cos of A minus B, right? So use this technique and get the values of this m of t. So here is your m of t, and now you can just convert into the Fourier, the frequency domain, you will get this value. So this is nothing, this is your Fourier transform, right? So this is the final result for your double sideband, right? Okay, so how exactly we are going to perform, how can we do it, how can we achieve the modulated signal? So this is your message signal, and this is your carrier wave. Of course you can see message signal have very less frequency, carrier have the very high frequency, and we are going to vary the carrier wave according to the message information, right? And so how can we achieve it? So here is your m of t, and so this is your actually m of t. So DSB SC modulator is there, and once m of t and the cos of omega, this is your carrier wave, this is your message wave. So here you will get the x1t, that is your m of t, and into the cos of omega ct, and here also you can get the x2t, and here is your nonlinear modulator here, so you can get the y of t. Since this is nonlinear modulator, so you will get the x1 and the ax square plus ax plus b of x square, right? So like that, and then finally if we'll pass it through the band pass filter, we will get the particular modulated wave. So the calculations details are here. Yt, like yt, since this is non-modulator, so axt plus b of x square t, right? First order only. Similarly we can also add b of x3, but we are avoiding cube term, and because we are always we have the band pass filter, so anyway we are going to reject that one. Okay, so then how can we find out this z of t? So use this nonlinear equation and put it from here, and then from here also you can get y1t minus y2t. Here this is your subtraction, so y1t minus y of 2t. So y1 is equal to, just here replace axt plus b of x1 square, and for y2 here it will be ax2 and bx2. Then put the values of m of t and carrier. You will get z of t will be 2am t plus 4bm cos of omega ct. Because a square plus b square and plus a square plus b square here, so both the other terms will cancel out, and 2am and plus 2am both will be added, so it is 4pm, right? Okay, so finally, this is your here it contains the m of t, right? And here also it contains the m of t to cos omega t. So this is masses, original masses only, and here is your masses into what? Into the carrier. So that is the modulated wave. So modulated wave is nothing, masses into carrier. So how can we achieve this masses into carrier? So this is one actual practical example, right? So using this. And now what are the examples of nonlinear modulator? So maybe your diode or transistor, right? So because your diode curve is varying non-modulating, right? Okay, so this is also called the single balanced modulator. Now, what is the modulation index? So we can find out. So this is your modulated wave. So under the modulated wave, you can observe the V, the carrier wave is varying from particular wave, the for a particular from amplitude to higher amplitude. So we will find out the V max and V mean. So after finding V max and V mean, we can find out the modulation index, that is V max by V divided by V max plus V. That is called the modulation index. So degrees of the modulation index. So modulation index M may have the three different values. Either it may be M is equal to less than 1. So that is called under modulation. M is equal to 1. This is called the critical modulation, and if it is greater than 1, that is called the over modulation. Of course, in case of the over modulation, you can check it here, like this is in terms of the negative carrier wave frequency, wavelength, amplitude. So that is why that you may lost the information exactly. So this is not perfect one, this is better, right? So these are the modulation. Now you can also find out the power, right? So how can we find out the power? So here is your sideband and carrier power. So here you can check the we can write the modulated wave is equal to a cos omega ct plus of mt cos of omega ct. This is your carrier wave and this is your modulated sideband, right? So this is the unnecessary the part we are sending. How? Because it will contains the power. So pc is your a square by 2 here for this, that is for carrier wave. Similarly for carrier wave for this signal, that is m square t divided by 2. So you can find out the eta, that is useful power divided by the total power. Why useful power? Because this part only contains the information, this will not have any information. Why? Because this is only the carrier wave. Okay, so useful, that is ps divided by ps plus p of c, right? So here m square divided by a square plus m square t, and m, that is your modulation index, which can also be written as your mu mt is equal to mu a into cos of omega t. Finally, if we'll get the modulation index, it can be written and eta is equal to mu square divided by 2 plus mu square, right? So for maximum value, if you wanted to calculate for your this DSB, here maximum is 33%, right? Similarly, you can find out the eta for different types of the signals, different types of the modulator. Here is one of the example for your SSB AM signal, that is single sideband modulated, right? So this is your M of T, or in frequency domain, this is your massive signal, that is M of omega. I'm up, and here this is your right one, here your left one. So this will also contains the same information, right? And this will also contain the same information. So in order to avoid the the frequency, we wanted to use only this part. So that is our objective. Now how we are going to use it? So here is the mathematical calculations, you can check it. So we are using like how can we reduce? So multiply with some function so that it will send to only from 0 to b. So that is also we are using the signum function, right? So signum function will be valid only for the 0 to if it is omega is greater than 0, then it will have the minus j, and if omega is less than 0, it will have j. So we are going to use this signum function. And this is your Hilbert transform, right? So Hilbert transform is nothing, that is m of t into 1 by pi of t. So if you multiply, you will get this Hilbert transform, right? So your USB signals will be your m of omega minus omega c, this one, and this is your omega plus omega c. This is the negative term, this is the negative term, this is your positive term, this is right. Now, how will be achieved? So in time domain, you can write that is m of t e to the power j omega t, and this is m of t e to the power minus j omega t. So you can also write for time domain m of t cos omega t and minus of m of Hilbert transform t and sine of omega t. This is for USB, and similarly for LSB, here it will be plus, right? So this is the technique to find out the SSB, that is single sideband. Here is your another modulation technique, Vestigial sideband. In the single sideband, what is happening? Like we may lost some information. So in order to avoid it, we are using Vestigial sideband here. So little bit more frequency we are going to transmit, right? So here your VSV can be m of omega plus omega c and m of minus omega c. Here we are using the sum h, that is the filter, so that it will send us some more information, right? So whatever this filter, so you can multiply with this, and the filter may be represented like 1 omega divided by h of omega plus omega c and h of omega minus omega c, right? So almost this is similar to SSB. How are we achieving? Simply m of t and just multiply it and use this your filter h1 of omega and filter out the remaining terms. You will get the VSV, and inside the demodulator again you have to multiply and pass it to the low pass filter. So we'll see the demodulation at the end of the session, that is how exactly it can be found. Okay, so now we are going to talk about the demodulation of AM waves. So this is your carrier wave, and here is your message information. So this is your E of t only suppose, and how can we remove these, and we can find out this spectrum only, right? So here is your modulated wave, that is m of t cos omega t, and again if we will multiply now with the cos omega t, then what will happen? It will shift your frequencies, and if we'll use the low pass filter, like suppose this is your low pass filter, we'll get the m of t. Calculations you can check here. This is also called the error t, that is error signal, that is m of t. Since it was your modulated is your m of t cos omega t, now we are going to multiply with the another cos of omega t. So that is why this is cos into cos square, right? And now cos square, you can you can use a formula to convert back. So here it will be 1 plus cos square 2 of t, so 1 by t, and so this is your, now we are going to get the m of t, right? So we can convert into the frequency domain, so 1 by 2 of e of m of omega, and this is your the shifted, so we will get this one. So this is our target to achieve, right? So this is also the demodulated signal. So this is the simple technique to get the demodulation signal. So how exactly we can achieve this demodulated signal? So one of the technique is envelope detector, right? So how can we get this envelope detector? Here is a circuit, AM modulated signal, and it will pass through this RC circuit, and we are going to collect this output across it, right? Load. So here we'll get. So how exactly your RC will vary depending on the values of RC. Actually, it will charge and discharge. So here it will discharge, again charge, here it will charge, again discharge, right? So in this manner we are going to get. So since we are the trying to get the envelope of the carrier wave, that is why this is called the envelope detector, right? So this ripple can be reduced by increasing the time constant RC, so that the capacitor discharge very little between the positive peaks, so it can increase the efficiency, the accuracy of machine. So here is the overview. So modulation techniques comparison. So primarily if you check that what are the types of the modulation signals we have discussed so far. So here is your DSB, SC, SSB and VSB, right? So what are these? So your DSB, SC means double sideband suppressed carrier, single sideband, and that is this is your Vestigial sideband. So here bandwidth for the DSB SC is your twice FM, for SCB, SSB your FM, and for VSB little bit less greater than FM, that is 1.25, right? Power efficiency is the not efficient this one, but still this is better compared to DSB, right? Because suppress carrier has been already suppressed. This is very efficient, but sometimes it may not be useful because it may lost some signal. This is moderate, but this is the best one, right? So applications for MSTers, then suppressed carrier, these are being used here. For long distance communication or HF radio, we are using SSB. For television, video transmission, all these we are using the VSB. So that's all in the sessions. If you have any doubt, you may drop your comments. Now we will come with another sessions where we are going to talk about the amplitude modulation. Thank you.